This is the first episode of the video lesson series on the laws of thermodynamics. Here we will study the zeroth law and the first law of thermodynamics. These are the intended learning outcomes of this lesson. As you can see, you are required to demonstrate higher order learning for this section. And this lesson partially supports you achieving learning outcomes 2, 4 and 7 of this module. Let's start with the zeroth law. The zeroth law introduces us a very important thermodynamic property called temperature. In our day-to-day works, temperature is the determining factor for the sensation of hotness and coldness. In thermodynamics, temperature is the driving force or the unbalanced potential that drives a flow of heat. Therefore, scientific meaning of temperature is at the heart of thermodynamics. The zeroth law of thermodynamics states that if two systems, let's say system A and B, are in thermal equilibrium, and one of those systems, for example, let's say system A, is in thermal equilibrium with a third system, that is system C, then all these three systems are in thermal equilibrium with each other. And all three systems have the same value for the property called temperature. And this is how the concept of temperature and thermal equilibrium were emerged from the zeroth law of thermodynamics. The zeroth law further establishes that the equality of temperature is the necessary and sufficient condition for thermal equilibrium. And it is with the introduction of the property temperature and the consequential condition for thermal equilibrium, the field of thermometry was meaningfully emerged. Thermometry is the technology of temperature sensing. I will talk about practical aspects of industrial temperature measurements in the lecture. Until then, here you have a question to try. List different types of commonly used temperature sensors available in the market with their applications. Please make sure your answer is available in the lecture for the discussion. Let us now move on to the first law of thermodynamics. This is also famously known as the law of conservation of energy. The first law establishes as a statement the behavior of the nature having energy as a conserved quantity. This is how the simple statement of the first law, the energy cannot be created and it cannot be destroyed, came in. And this is what you learned in your school as the first law of thermodynamics. However, in this undergraduate course, we are going to a bit more depth on the first law of thermodynamics. Like any other thermodynamic law, you cannot prove this mathematically. You simply have to accept this as a fact of the nature. The first explicit explanation of the first law said to have been made by the English physicist and mathematician Sir James Joule. The underpinning observations for the development of the first law had been made for closed systems undergoing thermodynamic cycles. However, you must clearly remember that the first law is a law of the nature, therefore it is not confined to closed systems or thermodynamic cycles. It can be applied just about anything in energy. This is what he observed and expressed as a law. When a system, that is a closed system, undergoes a thermodynamic cycle, the sum of the net heat supplied to the system from its surrounding and the net work input to the system from its surrounding must equal to 0. You can express this statement mathematically with this equation. This is the cyclic summation of heat transfer to the system, and this is the cyclic summation of the work transfer into the system. Summation of the cyclic summation of the two is equal to 0. This is the first law of thermodynamics. Because heat and work transfer can happen in both direction between the system and the surrounding. That is, heat and work is going into the system and heat and work going out of the system. In other words, heat is transferred to the system or heat is rejected from the system, and work is done on the system and work is done by the system. Therefore, it is very important to have a sign convention. There are different sign conventions being used in different textbooks. Here I am using one of these sign conventions, but it is completely free for you to adapt whatever the sign convention that you would like to adapt. However, you must make sure that you do not change the sign convention within a given analysis. That will obviously lead into errors. And also, do not leave any final answer with a sign. Like for example, heat transfer minus 200 kilojoule or work transfer minus 100 kilojoules. The minus and plus sign has absolutely no universal meaning. It has a reference to your sign convention. Therefore, you must explicitly indicate whether it is heat transferred to the system or heat rejected from the system, or work done on the system or work done by the system. That has to be explicitly indicated in your answers. The sign convention I am using here is heat transferred to the system is positive and work done by the system is positive. Heat rejected by the system, that is heat transferred from the system to the surrounding, is negative and work done on the system is negative. This is the sign convention I am adapting throughout this module. Before moving further ahead, let's check your understanding. There's a question here. In this question, a certain steam power plant, the turbine develops 1 megawatt. The power developed by the turbine is given as 1 megawatt. The heat supplied to steam in the boiler is 2800 kilojoules per kilogram. So that is a specific heat transfer. And the heat rejection, it is also specific heat rejection, that is 2100 kilojoules per kilogram. And the feed pump power required is also given as 5 kilowatt. You are required to calculate the steam flow rate. The first thing is you have to carefully think about this question and apply your knowledge of systems and draw the system boundary correctly, and then try the question. This is a question I have taken from this Applied Thermodynamics for Engineering Technologies book, and this question is worked out there. The answer given is 1.421 kilograms per second. See if you are getting the same answer or something very close to this. Pause this video and try this question and bring your solution into the lecture for discussion. The first law introduces 3 corollaries. The first corollary introduces the property internal energy, or broadly the energy of a closed system which is in equilibrium. The corollary says there exists a property of a closed system such that a change in its value is equal to the sum of the net heat and work transfer during any change of state. So this is a property whose value depends on the net heat and work transfer during a process. In an equation, we can write summation of heat and work transfer is equal to the change of the property. Because it is an unknown property, let us mark it as x. This corollary can be mathematically proven using the method of contradiction, but in order to do that one, you have to accept the validity of the first law of thermodynamics. Let's consider 2 independent thermodynamic processes. Process A and process B both bring state 1 to state 2. And let's take another third process, process C, which brings state 2 back to state 1, making two independent thermodynamic cycle, cycle AC and cycle BC. From the corollary, we can say the heat and work transfer in path A is equal to the change of the property X. Again, from the corollary, putting into the process B, we can say heat and work transfer along path B is equal to the change of the property. In order to prove that one, let us assume the converse of the proposition is true. That means the change of the quantity depends on the path. Only if it is independent of the path, then the change is identical. But here what we take is the change of the quantity depends on the path. You can apply the first law of thermodynamics to cycle AC and cycle BC. If you take cycle AC, the cyclic summation of heat and work transfer during the cycle AC must be equal to 0 from the first law of thermodynamics. When you consider cycle BC, the cyclic summation of heat and work transfer in the cycle BC is equal to 0. That is from the first law of thermodynamics. You can expand the cycles AC and BC because cycle AC consists of process A and process C. Therefore, the cyclic summation of heat and work transfer in cycle AC is equal heat and work transfer along path A plus heat and work transfer along path C. Similarly, the heat and work transfer in the cycle BC can be expressed as heat and work transfer along path B plus the heat and work transfer along path C. Now you can see in this equation, this term and this term are identical. Therefore, these two terms cancel out. Eventually, that will result in summation of heat and work transfer along path A is equal to the summation of heat and work transfer along path B. This is opposite to our assumption. Our assumption is heat and work transfer along path A is not equal to heat and work transfer along path B. Therefore, our assumption is wrong. That means the preposition is correct. And that property coming out from the corollary 1 is called the internal energy. So in an equation, you can write the summation of heat and work transfer is equal to change of internal energy for a closed system. The corollary number 2 says the internal energy of a closed system remain unchanged if the system is isolated from its surrounding. Here we are talking about isolated systems. You already know an isolated system is an extended version of a closed system where there is no even energy transfer, either as heat or work. This is quite obvious because if it is an isolated system, there is no heat transfer and there is no work transfer. Therefore, obviously, change of internal energy is equal to 0. This is in fact the corollary that brought the concept of conservation of energy. If you extrapolate your system to the universe, then you can say the total quantity of the energy in the universe is a constant. However, to make such an extrapolation, you have to consider the universe as a finite entity and you should be able to find the endpoint of the universe. However, this is far beyond our topic of engineering thermodynamics. Therefore, I am not going to discuss any further of this extending or extrapolating this into the universe. The corollary number 3 says that the perpetual motion machine of first kind is impossible. A perpetual motion machine of first kind is a machine that continuously produces work without any heat input while undergoing a thermodynamic cycle. Remember here, thermodynamic cycle. Like for example, you might be thinking, okay, you can compress a piston and after some time you can release it and then it produces some work output. But it is not a cycle. What this says is it should be operating on a thermodynamic cycle, that is continuously operating. Such a thing is not possible unless you provide a heat input. Actually, this can quite easily be understood from the first law of thermodynamics, because if heat transfer is 0, work transfer must be equal to 0. Therefore, perpetual motion machine of first kind is impossible. These are the three corollaries of the first law of thermodynamics. The conservation of energy implied by the first law of thermodynamics prescribes us to maintain a state of balance in all our interaction with energy in whatever the form it appears in. In other words, energy transactions in the form of heat, work, or energy transaction that takes place with mass transfer must be balanced by the change in the total quantity of the energy. We apply this generic expression into closed systems and open systems separately to derive more specific relationship for the energy balance for closed systems as well as open systems. Let us start with a closed system. You already know a closed system is a system where there is no mass transfer, but there can be energy transfer by means of either heat transfer or work transfer. This is a specific application of that generic statement into a closed system. Net energy transferred to the system as heat and work is equal net increase in the total energy of the system. It is obvious that if you supply heat and work onto the system, its energy content must be increased. If it is transferred from the system, then the energy content must be decreased. This expression can be presented as a mathematical equation like this. Basically, this is heat transfer to the system, which is positive, and work done by the system, which is positive. Therefore, if you deduct the work done by the system from the amount of heat transferred to the system, then the balance will indicate the net change of the total energy of the system. And total energy of the system comprises of the microscopic forms of energies plus the macroscopic forms of energies. And we already know in thermodynamic analysis, we take only kinetic energy and gravitational potential energy as the macroscopic forms of energy. We do not consider the chemical energy or nuclear energy or any magnetic potential energy, etc. in thermodynamic system, because those do not change in processes that we generally consider. This equation is also known as the non-flow energy equation of the first law of thermodynamics. Once again, you have to test your understanding before we are moving into open system. Try this question. In this question, it says in the cylinder of an air motor is a pneumatic motor, the compressed air has a specific internal energy 420 kilojoules per kg at the beginning, and after some expansion process, the internal energy has dropped to 200 kilojoules per kilogram. You are required to calculate the heat flow either to the system or from the system when the work done by the air during the expansion is 100 kilojoules per kilogram. The answer is 120 kilojoules per kilogram. See if you can get an answer closer to this value. Pause this video and try this question and bring your solution or any problem arise from doing this question into the lecture for discussion. Let us now apply the first law into open system. That is the energy balance for open systems. Since open systems are associated with mass transfer crossing the system boundary, a work is needed to push the mass or push the fluid into the system as well as from the system. When a mass is entering the system, the surrounding does this work on the system, whereas when the mass is pushed out from the control volume or the system does the work on the surrounding. To analyze this further, let us consider the fluid element enclosed by this red dotted line. This is an imaginary piston that is used to push this fluid into the control volume. And this is the pressure of the control volume which is exerting a force on this piston. So in order to move this mass into the system, you have to do a work against this pressure. This simple animation will elaborate what you are going to do. So you are pushing now this volume of fluid into the control volume against the pressure P. We can calculate the work required in order to do this one. The work done to enable the mass flow, that is equal force times this distance L, and the force is created by this pressure, that is equal to pressure times the cross-sectional area A. Therefore, the work required to push the fluid into the control volume, which is known as the flow work, because that is the work required to maintain the flow. Flow work is the technical term we use to explain that work. That is equal pressure times cross-sectional area times the length. And cross-sectional area times the length is the volume. Therefore, flow work is equal pressure times volume. Specific flow work, that means you divide both sides by the mass, or you normalize the flow work to mass, then you will get the specific flow work is pressure times the specific volume. The work you done to push the mass into the control volume becomes an integral part of the energy of the control volume, or it becomes a part of the energy of the control volume. Therefore, the total specific energy of a flow system comprises of the total energy of a non-flow system, which is denoted by E, plus the flow work. This is because flow work becomes a part of the energy of the control volume, because you are doing a work on the system in order to push the mass into the system. Similarly, you are doing a work on the surrounding when you are pushing the fluid out of the control volume. Then the specific total energy of a flow system, which is denoted by theta, is equal internal energy, specific internal energy, plus specific kinetic energy, plus specific gravitational potential energy, and the specific flow work. The summation of internal energy and the product of PV is the enthalpy. Therefore, we can specify the total specific energy of a flow system is enthalpy plus specific kinetic energy plus the specific gravitational potential energy. In an open system, enthalpy is the amount of energy that is transferred across the system boundary by a moving fluid. And as you can see, this enthalpy composed of internal energy and the flow work. Unlike a closed system where the only means of energy interaction with the system is heat and work, in an open system, the energy can cross the system boundary with the mass transport as well. For example, energy can come into the system with the mass. At the same time, energy can go out of the system with the mass when the mass is leaving the control volume. Our energy balance equation will have two additional terms. This is the term associated with the closed systems. Total energy crossing the system boundary or the control volume as heat and work. In addition to that, energy is brought into the control volume by the mass when it is entering, and energy is taken out of the control volume by the mass when it is leaving. That is equal to the net change in energy of the control volume. This can be expressed as an equation like this. There is a heat transfer, there is a heat supplied to the system minus work done by the system, plus this is the total quantity of energy transferred to the system with mass, and this is the total quantity of energy taken out from the system with mass. The sigma or summation is appearing here because a system can have multiple inlets as well as multiple outlets. Before we further develop this relationship, we need to be familiar with a couple of relevant concepts which will help us to simplify our energy balance equation for open systems. Transient and steady state are two important concepts. For example, in this diagram, you can consider this vertical axis represent any property, any thermodynamic property, and horizontal axis is the time. You can see in this transient part, properties are changing with time. In this case, it is fluctuating. In certain case, it is steadily growing or steadily declining. In the steady state period, properties do not change with time. That is the definition of steady state. In the steady state, properties do not change with time. This will help us to simplify our energy balance equation for open system. In fact, it is not just mere simplification, but it's more like the practical application. For example, if you take a steam turbine, we are not quite interested on its behavior at the starting cycle as well as shutting down cycle. What we are more interested on the steam turbine is the period where it is providing us the electricity. So that is steady state situation. We can assume the turbine is operating in a steady state manner. Likewise, many engineering devices, while it is in normal operation, we can consider it is operating in a steady state manner. So steady state means properties do not change with time. A steady flow process is a process where the fluid properties do not change with time at a given particular point. So properties may change from one point to another. If you take the system like this, the properties here may be different to properties there. Like for example, if it is an open system, there is an inlet, this is the outlet. Properties at the inlet may be different to properties at the outlet. But if you take a particular cross section, particular point, then properties do not change with time. That is called a steady flow process. In a steady flow process, we take properties at the boundaries do not change with time, right? At the boundaries do not change with time. Also, we take heat and work interaction between system and the surrounding do not change with time. With these characteristics, we can get back to our energy balance equation for open system. If the system is in steady state or if it is a steady flow process, net change in the energy of the control volume must be zero. Because if the energy in the control volume changes, property changes with time. That means it can't be in a steady state, or it can't be a steady flow. If it is a steady flow, all properties must remain invariable with time. Therefore, net change of the energy of the control volume equals to 0. Then our equation simplifies to net heat and work transfer is equal to the amount of energy brought out from the control volume with the mass minus amount of energy transferred into the system with the mass. You can further introduce the rate of heat and work transfer because that is more important for us in engineering analysis. Therefore, you differentiate all with respect to time. Then you get the rate of heat transfer, rate of work transfer, which is equal to the rate of mass transfer in exit and the rate of mass transfer at the inlet. And this is the flow energy, the total energy of a flowing fluid. At the same time, many engineering devices like, for example, turbines, pumps, or nozzles and diffusers, etc., can easily be modeled to have a single inlet and single outlet like this. Therefore, rather than having multiple outlet, many engineering devices are having single inlet and single outlet. Therefore, our equation can be further simplified. The summation of the mass transfer at the exit and summation of the mass transfer at the inlet are identical, which is mass transfer simply. Therefore, our equation further reduces into this form. But in engineering analysis, we are often working with specific quantities. Therefore, rather than having the total rate of heat transfer and total rate of work transfer, we can say the specific heat transfer and the specific work transfer, and right side you have the specific enthalpy, specific kinetic energy and specific gravitational potential energy. This equation is known as the steady flow energy equation. This is the energy balance for open systems which are having single inlet and single outlet, as well as the process is a steady flow process. This equation can be applied to analyze many engineering devices when they are operating in the steady flow manner, like turbines, pumps, compressors, nozzles, diffusers, so and so. This is a time for you to test your understanding. We talk about steady state. This question is, should a system be uniform to qualify for it to be in steady state? Think deep and develop an answer. And make sure you bring your answer to the lecture for a discussion. With that question, we are about to conclude this lesson. In this lesson, we talked about zeroth law of thermodynamics as well as the first law of thermodynamics. From the zeroth law, we talk about temperature and thermal equilibrium. And also we learnt about corollaries of the first law. And we learnt about steady versus transient and also energy balance. And also we learnt perpetual motion machine of first kind, which is the third corollary of the first law of thermodynamics. If you did not understand anything, please replay this video as many times as you want until you fully understand the concept in its fullest depth. And this is a little exercise for me to understand your level of understanding. List the 3 most confusing concepts you learn in this particular lesson. You have to provide your answer via Moodle. I have put a question on the Moodle. I will go through your answers and then I will identify what are the common gaps in your class. Then we can discuss further to clarify your problems. And in the lecture, we will talk more about this topic as well as we talk about some of the applications, and let's try some difficult questions during the lecture. Thank you.